In today's video, we look at continuity. Now, continuity is a concept that was studied in pre-calculus. We will now formally study it and formally define what it means for a function to be continuous. First, we look at three graphs. We start with this graph right here, and we ask, is this function continuous? Well, remember from pre-calculus, the idea of continuity was essentially function is continuous if you can draw the curve of the graph without lifting your pencil. So here we can draw this line, but right here at x equals a, there's a hole. So we'd have to lift our pencil to skip that point and then continue. So at x equals a, this is not continuous, right? Because there is a hole at x equals a. In other words, f of a is undefined. So it would seem that in order for a function to be continuous, the function f of x would have to be defined everywhere. Okay? Let's now look at a second function, this one. Now notice here that f of a is now defined. So is it continuous now? Well, at a, we'd have to lift our pencil to jump in value. Right? So we draw. Now we have to lift our pencil to move up and then continue drawing. So even though f of a is now defined, this function is still not continuous, right? Because there's a jump. There's a jump in values at x equals a. In other words, f of x is approaching different values from the left and right. Of x equals a. Well, this now, from what we studied before, is the idea of a limit. In other words, the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x. Which of course means that the limit as x approaches a of f of x does not exist. So now let's look at our third and final function. Here we go. We have f of a is defined and the limit as x approaches a exists. Is it now continuous? Right, draw. Oh, we now have to lift our pencil to draw this point up here and then go back down to continue the line. So this is also not continuous, right? And this is because f of a does not lie on the curve. Okay? In other words, f of x is not approaching f of a. All right, so in terms of limit, that means that the limit as x approaches a of f of x is not f of a. With these three ideas in mind, we can now formally define what it means for a function to be continuous at a point. So we say that a function is continuous at a point A if and only if the following three conditions are satisfied. And those three conditions are the three conditions that we just examined. First, f of a must be defined. Right? Because the first graph showed that if f of a is undefined, then the function is not continuous. Second, the limit as x approaches a of f of x must exist, because the second graph showed that if the limit does not exist, then the function cannot be continuous. Furthermore, third, the limit as x approaches a of f of x must equal f of a. The third graph showed that if it doesn't, then it can't be continuous. We say that a function is discontinuous at a point A if it is not continuous. That is, if it fails to be continuous. So if it fails one of those three conditions. Now, there are going to be three types of discontinuities we study in this course. First up, we say that f has a removable discontinuity. At the point A, if the limit as x approaches a of f of x exists, but the limit does not equal f of a. So if the limit exists, but it does not equal f of a, it is known as a removable discontinuity. F has a jump discontinuity at A if the two one-sided limits exist but they are not equal. Finally, F has an infinite discontinuity at A if one of the one-sided limits is infinite. And down here we have examples of each type. So here we have a removable discontinuity. Here we have a jump discontinuity. And here we have an infinite discontinuity. Now, the interesting thing about removable discontinuities is you can remove it by simply redefining the function. Right? So we can redefine f of x to be some function g of x f of x whenever x is not equal to a, and then we say it will be the limit as x approaches a of f of x when x is equal to a. Now we've redefined the function to remove the discontinuity. If we look at this middle graph now, if we were to ignore this portion up here, then wouldn't we have a continuous function? So this introduces the concept of one-sided continuity. Right? And there are two definitions for that. There is from the right and from the left. A function, let's say f of x, is said to be continuous from the right at the point A if the limit as x approaches A from the right of f of x is equal to f of A. And we have a very similar definition for continuous from the left. The only difference is now it's the left-handed limit of f of x is equal to f of A. So, if we come back up and we look at this jump discontinuity again, this would actually be continuous from the left, right? Because here's our limit. That is equal to f of A, right? Because it's a filled-in hole, or it's a filled-in dot. This is an open dot, right? That means that it is not defined at that point, so that limit does not equal f of A. We have so far discussed what it means for a function to be continuous at a point, but very rarely are we concerned with a single point. We want to know when is a function continuous over an interval. A function f of x is continuous on an open interval, and an open interval has the form AB with parentheses if it is continuous at every point in the interval. So to be continuous on an open interval, it has to be continuous at every single point in that interval. And of course, that uses the previous definition. We say it is continuous on a closed interval and remember that has the form AB but now with brackets. If it is continuous on the open interval A to B, it is continuous from the right at A and continuous from the left at B. Right, now try and think why it only has to be continuous from the right at A, and why it has to be only continuous from the left at B. We can form similar definitions for the two half-open intervals AB, where it's closed at A, and AB, where it's closed at B. So there are similar definitions for these two as well. All right, some properties of continuity. First up, if F and G are continuous, at x equals A, then so are the following. F plus or minus G, K times F, where K is a real number, F times G, and finally F over G, as long as G of A is not equal to 0. So in other words, if you take the sum or difference product of continuous functions, they are still continuous. If you take a constant multiple of a continuous function, it is still continuous. And if you take the quotient of continuous functions, it is continuous as long as what you're dividing by is not 0. Second, polynomial, rational, radical, exponential, logarithmic, trigonometric, and I'm going to stop with trigonometric functions. So all these types of functions are continuous over their entire domain. And finally, the third, which is one of the more important results, this is known as the composite function theorem. All right, so this says if f of x is continuous at L and the limit as x approaches A of g of x is equal to L, then the limit as x approaches A, f of g of x is equal to f of L. In a sense, what this is saying is we can pull the limit inside of a continuous function. All right, the intermediate value theorem. Which is abbreviated the IVT. This states, let f be continuous over a closed bounded interval AB. If Z is any number that is between f of A and f of B, then there is a number C located in the closed interval AB such that f of C is equal to Z. Now, we shall not prove this here. The proof is quite technical, and it requires some advanced techniques that we do not yet have. However, we can look at what it's saying graphically. Right? So we have a continuous function here, f. We're only going to consider this blue segment here, which is between A and B. Right? So it's continuous over the closed interval AB. Notice that it's also a bounded interval, meaning that it can't just go off to either plus or minus infinity. Now it says that if Z is any number between f of A and f of B, right, so here we have f of A, here we have f of B, here's Z, then there has to be a number C in the closed interval AB such that f of C is equal to Z. So there has to be a number in the interval that will evaluate out to Z. Right? And that makes sense if it's continuous. Right? In this case, here's our Z. We draw the line. There would be our C. Notice that what this theorem is saying is it's only guaranteeing the existence of such a number. It is not telling us how to find said value C. Only that it exists, and only that at least one exists. There could be multiple values, right? But this guarantees that at least one of them exists. Now, when trying to determine whether a function is continuous at a point, there are 3 steps that should be taken, and they come right from the definition. First thing we should do is check to see if f of A is defined. If it is undefined, then we're done, right? The function is not continuous at x equals A. If, however, it is continuous at A, we then check to see if the limit as x approaches A of f of x exists. If it does not exist, we're done. The function is not continuous. If the limit does exist, we check to see if that limit is equal to f of A. If they are not the same, the function is not continuous. If they are the same, then the function is continuous. We will now conclude this video by looking at several examples. The first example we will determine whether this function, f of x, which is going to be a piecewise function, negative x squared plus 4 when x is less than or equal to 3, and 4x minus 8 whenever x is greater than 3, whether it's continuous at x equals 3. So first thing we have to do is decide, or is check, does f of 3 exist? All right, so f of 3. Well, we have to throw it in to this top piece, right? Right? X less than or equal to 3. Since x equals 3, it goes in here. We get negative 3 squared plus 4, which is negative 5. So it exists. Next, we have to check, does the limit at 3 exist? Since this is piecewise, we have to look at the one-sided limits. So let's start with the left-handed limit. Now again, this is the left-handed limit. So the piece that we're using is the piece for less than 3. So negative x squared plus 4. This just gives us negative 5. Next up, we check limit from the right. So since this is a right-handed limit, we will use the piece for x greater than 3. This will give us 4 times 3 minus 8, which is 12 minus 8, which is 4. These two limits are not the same. So the limit as x approaches 3 of f of x does not exist, which immediately means that f of x is discontinuous at x equals 3. It is, however, continuous from the left. Next up, we'll use the composite function theorem to evaluate the limit as x approaches pi over 2, cosine of x minus pi over 2. Now remember, what this says is we want to look at the limit as x approaches pi over 2 of x minus pi over 2. That is 0. If cosine is continuous at 0, which it is, right? Because cosine is continuous over its entire domain, which is all real numbers. We can just say this: the limit as x approaches pi over 2 of cosine of x minus pi over 2 is the cosine of the limit as x approaches pi over 2 of x minus pi over 2, which is cosine of 0, and cosine of 0 is 1. So that is what the composite function theorem is saying. Finally, we will show that f of x equals x minus cosine of x has at least one 0. Now, to do this, first notice f of 0. 0 minus cosine of 0, which is equal to negative 1. Let's take a look at f of pi over 2. Right, so this is pi over 2 minus cosine of pi over 2. Well, since cosine of pi over 2 is 0, this just gives us pi over 2. Now, since x and cosine of x are continuous everywhere, right? Because x is a polynomial, and its domain is all real numbers, so it's continuous over all real numbers. Then f of x would also be continuous everywhere. Right? That is by this first property that we studied right up here. Well, what this is saying then is since it's continuous everywhere, more specifically, it is continuous on the interval 0 to pi over 2. Now, since 0 lies between -1 and pi over 2, the intermediate value theorem says that there must exist some value c in that interval 0 to pi over 2 such that f of c is equal to 0. That is what we wanted, right? We've shown that this function must have at least one 0. In other words, this function will cross the x-axis in at least one point. Specifically, we've shown that it's going to have to cross the x-axis somewhere between 0 and pi over 2. Now, it could cross in other locations as well, right? But we're not interested in that. We just wanted to show that it's going to cross at least once. Now, that concludes our video on continuity. In the next video, we will look at limits at infinity. The video after that will then be the precise definition of the limit.